Thank you for clicking into this video. We are from Group 3 and today we are going to be talking about Knapsack problem. In Group 3, the leader is Foong Weng Yau, 289851. The members are Chong Kar Min, 287173, Tracy Liaw, 287944, and Low Wei Jie, 289669. My name is Tracy Liaw with matrix number 287944, and I'll be starting off with the introduction. So, what is Knapsack problem? Knapsack problem is a fundamental optimization challenge that seeks to identify the most valuable combinations of items to include in a knapsack without surpassing its capacity. So the primary goal of solving a knapsack problem is to maximize the total values for the total weight does not exceed the capacity. There is a total 4 types of knapsack problem, including the fractional knapsack problem, the 0-1 knapsack problem, the bounded knapsack problem, as well as the unbounded knapsack problem.
Let me introduce about what is an exhaustive search. Exhaustive search is a brute force approach to find out the elements from combinatorial objects like permutations, combinations, or subsets of a set. This technique can generate all possible subsets of items and evaluates each to determine the most valuable one that can fit within the knapsack's capacity. Why I'm gonna choose this exhaustive search? It's due to its simplicity and accurateness. First, it offers a straightforward implementation which enable us easier to conceptualize encodes. By systematically generating all possible subsets of items, we can ensure that we explore every potential combinations, leaving no possibility unexamined. Next, it guarantees an optimal solutions, because a thorough exploration ensures that no better solution is overlooked, giving us the confidence that we have indeed found the most valuable subset. Next, here is the algorithm for exhaustive search. The flow is somehow like: first, it generates all possible subsets of items, and for each subset, calculates its total weight and value. Next, this algorithm identifies the feasible subsets by gaining the total weight, which must be smaller or equal to the knapsack capacity. Finally, it selects the subset which is an optimal solution with the highest value among the feasible subsets.
Good day, madam. My name is Low Wei Jie with matrix number 289669. So I'm going to explain about the dynamic programming. Dynamic programming is a technique for solving the problems with overlapping subproblems. Typically, these subproblems arise from a recurrence relating a given problem solution to solutions of its smaller subproblems. Rather than solving overlapping subproblems again and again, dynamic programming suggests solving each of the smaller subproblems only once and recording the results in a table from which a solution to the original problem can then be obtained. And there are bottom-up dynamic programming approach which solve all the smaller subproblems of a given problem, while top-down variation of dynamic programming seeks to avoid solving unnecessary subproblems. Whether one uses which version of the dynamic programming algorithm, the crucial step in designing such an algorithm remains the same. It's still required to derive a recurrence relating a solution to the problems to solution to its smaller subproblem. Dynamic programming exploits the properties of optimal substructure, which means an optimal solution to a larger problem can be constructed from optimal solution of its smaller subproblems. By storing and reusing the solutions to its subproblems, dynamic programming avoids redundant computations and dramatically reduces the overall computational time. So, the reason we choose dynamic programming to solve the knapsack problems are: first, its efficiency stems from the bottom-up approach. We start by solving the smaller subproblems and gradually build up to solve the main problem. The solutions to these subproblems are calculated only once and then reused to derive solutions for larger subproblems. This optimized reuse of solutions significantly reduces time complexity and improves overall algorithm performance. Second, dynamic programming excels in scalability when handling larger instances of the knapsack problem. As the number of items and capacity constraints increase, the problem space grows exponentially. However, the dynamic programming systematic approach to tackling the subproblems and storing their solutions allows it to effectively handle larger instances. It efficiently scales with the size of the problems, making it a practical and reliable choice for the real-world scenarios involving numerous items and complex constraints. For the algorithm to solve the knapsack problem using dynamic programming, we have to create some variables for it, which are n, which refer to the length of the weight, array of the weight, array of the value, the knapsack capacity, and an array table. There are basically 5 lines of the algorithm for the dynamic programming. First and second line of the algorithm are nested loop, iterate through each item and possible knapsack capacity from 0 to the capacity. If the weight of the current item is greater than the current knapsack weight, we cannot include the current item in the knapsack without assessing its weight. Next, if the current knapsack weight is bigger than or equal to the current weight, the maximum value achieved for the given knapsack capacity is stored in the table of position I and J, and then continue back with the log. At the end, the table is fully filled and the table is returned.
The next part is the demonstration part. Given there's a knapsack question, and Team 3 will have to explain how to solve this question using exhaustive search and dynamic programming. Tracy and WengYau will be in charge of explaining the questions using the exhaustive search, while WeiJie and KarMin will be in charge of explaining the question in dynamic programming. So the question is, given 4 items and a bag with a capacity of 10. Find a way to fit as many things as possible. The first item has a weight of 5 and value of 30. The second item has a weight of 3 and value of 20. The third item has a weight of 8 and value of 40. The last item has a weight of 2 and a value of 10. So the first step is to count the possible combinations using exhaustive search. The formula is 2 to the power of total number of items. So in this case, we have 4 items, so it is 2 to the power of 4. And the possible combinations using exhaustive search is 16. When no item is put inside the bag, the total weight is 0 and the value is 0. When only item 1 is put inside the bag, the weight is 5 while the value is 30. When only item 2 is put inside the bag, the weight is 3 and the value is 20. When only item 3 is put inside the bag, the weight is 8 and the value is 40. When only item 4 is put inside the bag, the weight is 2 and the value is 10.
Now, I will continue the demonstration for exhaustive search. Starting from here, the demonstration is targeted to items. For the first and second item, the total weight is 8, while the total value is 50. For the first and the third item, the total weight is 5 plus 8 equal to 13, while the value is invisible. And then for the third combination, which is the first item and the fourth item, the total weight is 7, while the total value is 40. For the second and the third item, the weight is 3 plus 8 equal to 11, and the value is invisible. For the second and the fourth item, the total weight is 5, while the value is 30. For the third and the fourth item, the total weight is 10, while the value is 50. Next, I'll continue the exhaustive search which target for the 3 items. For the first, second, and third item, the total weight is 5 plus 3 plus 8, which is equal to 16, but the value is invisible. For the second combination, there are first, second, and fourth item. The total weight is 10, and it gives the value of 60. For the first, third, and the fourth items, the total weight is 15, and they give an output of invisible value. For the second, third, and fourth item, the total weight is 13, while the total value is invisible. And for the all of item, the total weight is 18, but it gives a result of invisible. For the question given is given 4 items and a bag with capacity of 10. Find a way to fit as many things as possible. So from the demonstration targeting the singles, 2 item and 3 item, the conclusion we get is the optimal solution is the subset of first, second, and fourth item putting in the bag, which has the highest total value of 60 compared to other subsets that can fit the knapsack's capacity.
For the demonstration part to solve the knapsack problem with dynamic programming, we got one sample with 4 elements and maximum capacity of 10. First step, we will create a 2D array, then initialize the first row with 0 value. Start with the first element. It will only store if the weight is greater than 5, so capacity of 0 to 4 is still 0. and start filling the capacity of 30 when weight is 5. Then fill the rest of the array in this row with 30. For the second element, the minimum weight is 3, so the capacity of 20 will start filling at the weight of 3. For weight of 4, it will also store 20 since it is not enough to store the first element with weight of 5. Row with weight of 5, 6, and 7 will store the capacity of 30 instead of 20. Because it will only store the maximum capacity, so 20 is not stored. Start by the weight of 8 is able to store both the element 1 and 2. The capacity stored is 20 plus 30, which is 50. Go to the element 3. The weight is 8, which is higher than the element 1 and 2, so the array in this row, which from 0 to 7, is still the same as the previous row. When it reaches the weight of 8, it chooses the maximum out of 50 or 40, so 50 is stored in this place. The weight of 9 and 10 is still the same as previous row.
Good day, madam. My name is Chong Kar Min, number matric 2877173. Now I will continue demonstrating the Knapsack problem by using the dynamic programming algorithm. As the weight for item 4 is 2, so we will start filling the 2D array from V42, which is the row number 4 and the column number 2, using the formula same as just now that explained by Low Wei Jie. The columns in front of V42 will be filled in the number of 0, like the previous row. Then we will compare the maximum value of V32, which is 0, and the 10 plus V30. V30 is 0, so 10 plus 0 is 10. So we compare 0 with 10. We will choose 10 to fill in the V42, which is the highest value. Next, for the V43, we will use the same formula as just now. We compare the maximum value of V33, which is 20, with 10 plus V31. V31 is 0, so 10 plus 0 is 10. We compare 20 with 10. So we will choose 20 to fill in the V43 as it is the highest value. Then for the V44, we will compare the maximum value of V34, which is 20, with 10 plus V32. V32 is 0, so 10 plus 0 is 10. 20 compared with 10, 20 is the highest value, so we will fill in 20 in the V44. After that, for the V45, we will compare the maximum value of V35, which is 30, with 10 plus V33. V33 is 20, so 10 plus 20 equal to 30. So the highest value is 30, and we will fill in the number of 30 in the V45, which is the row number 4, column number 5. Next, for the V46, we will compare the maximum value of V36, which is 30, with 10 plus V34. V34 is 20, 10 plus 20 is also equal to 30. The maximum value here is 30, so we will fill in number of 30 in the V46, which is the row number 4 and the column number 6. For the V47, we compare the maximum value of V37, which is 30, with 10 plus V35. V35 is 30, 10 plus 30 equal to 40. So we compare 30 with 40. 40 is the highest value, so we will fill in the number of 40 into the 2D array of V47. For the V48, we will compare the maximum value between the V38, which is 50, with 10 plus V36. V36 is 30, 10 plus 30 equal to 40. 50 compared with 40, 50 is the highest value. So we will fill in the number of 50 in the V48. Next, for the V49, we will compare the maximum value of V39 with 10 plus V37. So V37 is 30, 10 plus 30 is also equal to 40. 50 compared with 40, 50 is the highest value, so we will fill in the number of 50 into the 2D array of V49, which is the row number 4, column number 9. For the last column, V410, we will compare the maximum value of V310, which is 50, with 10 plus V38. V38 is 50, 10 plus 50 equal to 60. 60 is higher than 50, so we will fill in the number of 60 into the last column, V410. After completely filling the 2D array, we will find the optimal solution by using the backtracking method from the entry of V410, which is the last column in the 2D array. Since the V410 is 60 greater than V310 50, it implies that item 4 must be included in the optimal subset. Along with the item 4, we find an optimal subset for the remaining capacity of 10 minus 2 equal to 8, which is represented by V38. Since the V38 is equal to V28, item 3 is not included in the optimal subset. Then we compare V28 with V18. Since the V28 50 is greater than V18 30, item 2 is also the part of the optimal subset. Then the remaining capacity is 8 minus 3 equal to 5, which is represented by V15. Similarly, since the V1530 is greater than V050, item 1 is the final part of the optimal solution. As a result, the optimal solution is the subset of item 1, item 2, and item 4. It has the highest total value of 60, which is 30 plus 20 plus 10. That fits the snapshot capacity. This is because the total weight of item 1, item 2, and item 4 is 5 plus 3 plus 2 equal to 10. It does not exceed the snapshot capacity given before. Now, we will compare the runtime analysis of both algorithm techniques that were applied previously. For the exhaustive search algorithm, it explores all the possible subsets of items, leading to 2 power n subsets for a set of n items. With constant time operations to calculate the weight and value for each subset, the overall time complexity is big O 2 power of n. However, due to its exponential scope, it is only suitable for small snapshot instances. On the other hand, the dynamic programming algorithm employs a 2D array of size n plus 1 times w plus 1 to store the intermediate results. Each entry requires constant time computations with a time complexity of big O n times w, where n indicates the number of items available and the w indicates the capacity of the snapshot, making it more efficient for larger snapshot instances. We can see clearly the comparison of exhaustive search and dynamic programming in terms of time complexity from the graph given on the left-hand side. Besides that, in terms of efficiency, dynamic programming algorithm is much more efficient than the exhaustive search algorithm, especially for the larger problem indices. As the number of items increase, the dynamic programming algorithm scales much better and provides a solution in a reasonable amount of time. On the other hand, exhaustive search algorithm becomes computationally demanding and impractical for the larger indices because of its exponential time complexity. Therefore, exhaustive search algorithms is only suitable for the smaller snapshot problem, while the dynamic programming algorithms is able to solve the larger snapshot problem efficiently.
In conclusion, both methods are implementable when it comes to solving a knapsack problem. Exhaustive search guarantees to find the optimal solution. However, its exponential time complexity limits its feasibility for larger datasets. On the other hand, dynamic programming is more preferable and more efficient solution compared to exhaustive search because it has a constant time complexity. So that's all for the presentation for Group 3. Thank you for clicking into this video.